Mathematics made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Toidel online class. So today we want to look at homomorphism. So we want to look at homomorphism. We want to look at homomorphism. So as we have it on the board, so how do we define homomorphism? How do we define homomorphism? So as we have it on the board, our homomorphism is a mapping from one group into another, which preserves the structure in the group. That keyword is important. Of course, for you to have vast knowledge about this homomorphism, you must be conversant with the concept mapping. So you must be conversant with mapping. Mapping, if you can check my videos on mapping 1 and 2. So the only difference here is that in case of homomorphism, you know, when you have mapping like F, if let's say F map A into B under mapping, A and B are sets, they are ordinary sets, and F is the function or relation, okay, or the mapping. But in case of homomorphism now, homomorphism is also a mapping, but it's from one group to another. But here it's from one set to another. That's just the difference. If you have mapping at the elementary stage, we are just talking of the movement of is a function from one set to another. We call this domain, we call this codomain. Okay, so the relation here, or you can write it this way: say A to B. Then you put the relation here or the mapping. That is that about mapping. Please check my videos. I have 2 videos on mapping, so you must understand mapping very well. Types of mapping before we have proper understanding about this concept. Homomorphism. Homomorphism is a mapping from one group. So we are talking about group now. And of course, if you say a group is a set, is a non-empty set plus a binary operation. This binary operation will actually perform, these operations will perform on the element of this set. Okay, so that's the difference between ordinary sets and a group. A group is also a set, but a set that has a binary operation. Okay, so homomorphism is a mapping from one group into another, which preserves the structure in the groups. Now let's see. Let H, asterisk and K, plus be 2 groups. And look at, this is the mapping. This is the mapping between the group. And F, such that H, it takes element from H to K, is a mapping such that for all A, B, all the elements A and B is coming from this set of this group. It's coming from this group. A, B belongs to H. If we can get F of A asterisk B to be equal to F of A plus B, we talk about preservation of the structure. The domain here now, it is asterisk, that's binary operation. Then the codomain, the one here, it is plus in a circle, inscribed in a circle, that is binary operation. So now look at, for us to be able to have a homomorphism, this left hand side, which is from here, must be asterisk. Then this other side must be the binary operation there. So if you're able to write this, then we say F is called homomorphism. So that's just introduction to homomorphism. In case of homomorphism, homomorphism is also a set. Homomorphism is also a mapping, but it's a mapping from one group to another. So homomorphism is a mapping from one group to another. So we should note that. Let's know that homomorphism is a mapping from one group to another. So that is that about homomorphism. Then let's define what is called a kernel. Definition. There's what we call a kernel. The kernel of F. Kernel of that mapping. So let's see. Let F such that it takes X to Y be a homomorphism. Of course, you know the meaning of homomorphism now. Be a homomorphism. Full stop. Be of homomorphism. Full stop. Then the kernel spelled Kernel. Then the kernel of F denoted by Kf is the set of elements. The set of elements of X is the set of elements of X which are mapped is a set of elements in X which are mapped onto the identity in Y. So what do I mean by that? If you have to define a kernel of F is homomorphism, and we know the meaning of homomorphism. So what do I mean by that? Kernel of F, as we have it, is given as X that belongs to X, such that F of X, the homomorphism, must give us the identity. That is, where E subscript gamma or Y is equal to identity in Y. So that's that about the kernel. For us to have a kernel of this homomorphism, this mapping F is called homomorphism. We know the meaning of homomorphism now. Homomorphism, we know the meaning of homomorphism, is a mapping from one group to another group. And that mapping must preserve the structure of that group. So F is no longer ordinary mapping, but it's called homomorphism. Okay? Then when do we say that F is a kernel? F will be a kernel where we have X and Y here. They are not ordinary set. These are groups. They are groups. They have binary operation. But since we know that homomorphism we know that homomorphism is a mapping between two groups. So we can just forget about the binary operation and just write X and Y without any structure. Because we know that under homomorphism, the structure is preserved. So since we know, then we say let F such that X to Y be a homomorphism. Then the kernel of F, denoted by Kf, is the set of elements of X. That is, you take element from this X. Say X from this X. It is a set of elements of X which are mapped onto the identity of Y. Of course, please check my video on mapping. You know, we have onto mapping. That is surjective. Then we have injective mapping. That's one-on-one. Then we have bijective. Bijective is when we have one-on-one and onto. So please check my video on that and have proper understanding about mapping. So let's take example. I want us to take example. Let's take example on homomorphism before we talk about types of homomorphism. Let's take an example on homomorphism before we go ahead and talk about types of homomorphism. So I want us to take example on homomorphism. So let's take example. Example. Let's say example 1. So the question says determine whether or not each of the following mappings is a homomorphism. Of course, by now we all know that homomorphism is not ordinary mapping. It's a mapping of a group. It's a mapping of groups from one group to another. The first one is when you have f to be equal to integer under addition tends to real number under addition. That is how f is defined. Then it is given by f of x is equal to 3x. And let's see the second one, where we have f such that integers under addition. Of course, these are groups. This is a group. This is another group. Addition given by f of x is equal to 3x plus 4. Then let's take one more, where we have set of real numbers under addition to set of real numbers, positive real numbers under multiplication. This is ordinary real number under addition. Then this set of positive real numbers under multiplication, and it's given by h of x is equal to 3 raised by x. So we want to show either whether f is homomorphism or not. So we take it one after the other. So we are going to take it one after the other. So the first one, what do we have? That first one, we have f z plus to real number plus. So this is what we have, and f of x is defined as what? 3x. So what do we show? So what we want to show here is that this is addition and this is also addition. Please look at it. This is addition. The structure here must be preserved. So the binary operation here is addition. The one here is also addition. So no problem. Here is addition. But this third one, we have addition and multiplication. We are going to see the implication now. So the function, that mapping f of x is defined as 3x. So how do we show that this f is homomorphism? We now say f of a plus b, that is, when we pick two elements from z, this z under addition. What is f of x? F of x is 3x. What is f of a plus b? Where a and b are elements from z. Then this will be 3 into bracket a plus b. Please, let's look at it very well. And this is going to give us 3a plus 3b. So will this give us the same thing as saying f of a plus f of b? So f of a will be 3a plus 3b. Okay. Do we get the same thing? Yes. You now say, therefore, since f of a plus b is equal to f of a plus f of b, since this holds, then we say thus f is a homomorphism. So that's how we conclude. Let's look at it very well. Look at what we have there very well. Under the definition of homomorphism, under the definition of homomorphism, that's what we are given. Under the definition, where we are given asterisk and plus, the condition is that f of a asterisk b must give us f of a plus f of b. That's the condition from the definition. So that's the condition from the definition. So please, let's look at it very well. So in this case now, this is addition, this is addition. So we look at it. If we take it together like this, f of a plus b, are we going to get the same thing as taking it separately? If we're able to get the same thing, then it shows that f is a homomorphism. So we go ahead and we go to the second example. We go to the second example and test if it's a homomorphism or not. So let's go to the second example. The second example is where we have f to be z plus tends to r plus. Then in this case now, we have f of x to be equal to 3x plus 4. That's what we have. Okay. So we are going to show for f of a plus b, because this is plus for plus. So in this case now, where we have x here, just change it to a plus b. We are going to have 3 into bracket a plus b plus 4. Then here we have 3a plus 3b plus 4. That's what we have at the left hand side. Then are we going to get the same thing as saying f of a plus f of b? That is the one we have at the right hand side. So if we are able to show that they are the same, then we say that f is homomorphism. If not, we make our conclusion. Then let's see f of a. Okay, this is f of a plus f of b plus f of b. Here, f of a will be 3a plus 4. Then plus f of b will be 3b plus 4. At the end of the day, we have 3a plus 3b plus 8. 4 plus 4 is 8. So from there, what can we conclude? F of a plus b plus f of a is not equal to f of a plus f of b. Look at in this case now, we didn't get the same answer. This answer and this answer, they are not the same. Since they are not the same, then we make a conclusion that thus we make a conclusion that f is not homomorphism. That will be our condition there. So we make a conclusion that f is not homomorphism. So that is our conclusion. Then we go to the third one. The third example, which is last example, before we consider types, before we consider types of homomorphism. So we go to the third one before we consider types of homomorphism. So let's take this third one. In this third one now, we can try to change this f. We can call it h. We can call it anything, any letter. Let's use h. H is equal to r under addition to positive r under multiplication. That's what we are given. Then h of s is defined as 3x, 3 raised by x. That's what we are given. We want to check if this is homomorphism. Look at here. At the left hand side now, what we have here will be addition. Then this other one will be multiplication. They are not the same. You see the implication of what I'm talking about now. That is the difference between ordinary mapping and homomorphism. Homomorphism is both elements in order homomorphism must be a group. And when we are talking about a group, we must preserve the structure. In this case now, the structure here is positive and multiplication. That is the structure here. So what do we have here? The first one, we look for h of a plus b, because what you have here is addition. Then this is going to give me 3 h of a. H of x is 3 raised by s. H of a plus b will be 3a plus b. And of course, from the law of indices, I can split this to be 3a multiplied by 3b. It's possible from the law of indices. Then what do I have at the right hand side? At the right hand side, this is multiplication. I'm going to have h of a multiplied by h of b. That's what I'm going to get. Look at the first example and second example. Everything is plus plus, so we are on the same side. But in this case now, everything is not plus plus. So one is plus. We must preserve the structure. This is plus and this is multiplication. So we have applied that of plus. We go ahead and apply that of positive. But what we have here is also positive. I'm going to write plus here. But the structure, what we have here is multiplication. So I change this to multiplication. So what is h of a? H of a is 3 raised by a multiplied by 3 raised by b. What can you say about the two? We say h of a plus b is equal to h of a times h of b. So since we are able to get the same thing, then we now say thus h is a homomorphism. So h is homomorphism. That is how to test for homomorphism. That's how to test. So after this now, we can go ahead and talk about types of homomorphism. There are 5 types of homomorphism. Types of homomorphism. Types of homomorphism. Basically, we have 5 types. We have 5 types of homomorphism. We have 5 types of homomorphism. Then the first one that we talk about is called an endomorphism. That's the first type of homomorphism. So what do we understand by this endomorphism? An endomorphism is a homomorphism. Is a homomorphism. Homomorphism is an homomorphism from a group into itself. So this first type of which is called an endomorphism is a homomorphism from a group to itself. So if you are asked to define an endomorphism, just say that an endomorphism is an homomorphism from a group to itself. That is, if you say let G be a group, let G be a group, let G be a group, and F, the homomorphism now, it will be from G to G. Of course, we didn't put any structure here, either addition or what. We didn't put the binary operation. But since we talk about homomorphism, we know that homomorphism is a group. It's not a set. It's a group. So we say let G be a group. Let G be a group, and F, the homomorphism, is from one group to itself, G to G. Okay. A mapping and F from G to G, a mapping such that we'll be able to see is a mapping such that, let me write here, is a mapping such that F of AB is equal to F of A multiplied by F of B for all AB belongs to G. Then F is an endomorphism. So that's the definition of endomorphism. Endomorphism is a homomorphism from a group into itself. That is, when we have a group into itself, it is called endomorphism. Then we go ahead and talk about the second types of homomorphism, and it is called a monomorphism. A monomorphism. So what do we understand by monomorphism? This is the second type of homomorphism. So a monomorphism is an injective homomorphism. That is, a homomorphism is an injective. Of course, under mapping, injective simply means one-to-one. It's an injective homomorphism. So if you check my video on mapping, there are three types. No, there are three basic types. We can have more than that. We have one-to-one, onto, and bijective. So this one is injective, onto is surjective, then bijective is both. Okay. So in case of monomorphism, a monomorphism is an injective homomorphism. That's the definition. That is, we say let. Then I want to explain further now. We say let G and H be groups, and F such that take an element from G to H. Look at, in this case, we have G to G under endomorphism, group into itself. But under monomorphism is from G to another group, H. So that's what we have. So let this be a mapping. Let this be a mapping such that Roman figure 1. We have for all AB that belongs to G, we can have F of AB that will be equal to F of A multiplied by F of B. That's the first condition. That is the first condition under monomorphism. That is, we want to talk about one-to-one. That's the first condition. Then the second one simply means that for all AB that belongs to G, so we know that F of A will be equal to F of B, because this is one-to-one arrangement, which implies that A is equal to B, and F f of A is not equal to f of B, and f of A is not equal to B, which implies that A is not equal to B. So then we say F is a monomorphism. Monomorphism. So we are going to take example on this. It's a monomorphism from G into H. That's what we conclude. Under endomorphism is from G to G. So it's from G to G under monomorphism. Under endomorphism, but under monomorphism, a monomorphism is an injective, is a one-to-one monomorphism. And a monomorphism is an injective, homomorphism. That is one-to-one. So that is the definition of monomorphism. Then we take the third one. The third one is called an epimorphism. The third one is called an epimorphism. An epimorphism. So what do we understand by epimorphism? This is an onto monomorphism. That is a subjective homomorphism. So an epimorphism is a subjective, which is onto. It's a subjective. This is a subjective homomorphism. Please let's note the difference between all these. Monomorphism is injective, that's one-to-one. So this epimorphism is an injective, is a subjective homomorphism. So this one is onto. It is called onto. It's an onto homomorphism. So let's explain further. Let G and H be groups, and F such that G to H a mapping such that the first condition under one to down is that for all AB that belongs to G, we can have F of AB to be equal to F of A, F of B. That's the first one. That's the first condition. Then the second condition is that there exists H that belongs to H, the codomain. There exists H, for all, no, not that exists. For all H that belongs to H, there exists G that belongs to G, such that F of G is equal to H. And of course, this condition, these are the conditions that we consider under subjective mapping. The only difference here is that under subjective mapping, when you check my video on mapping, F will be subjective. These are ordinary sets, no preservation, ordinary sets without binary operation. But under monomorphism, all this epimorphism stuff, F and G are groups. They are not ordinary sets, they are groups, because there are some conditions they satisfied. We have done that in the previous class. So an epimorphism is a subjective homomorphism. Then if these two conditions for subjective onto holds, then F is an epimorphism. It's an epimorphism from G onto H. So we talk about the fourth one, which is called an isomorphism. This is the fourth type of homomorphism, an isomorphism. How do we define an isomorphism? An isomorphism is a bijective. It's a bijective, that is both one-to-one. Bijective simply is both one-to-one and onto. So an isomorphism is a bijective homomorphism. The two conditions that we have in 3 and 4 must be satisfied there. So we can explain further to say let G and H be groups, and F from G to H a mapping such that let's see the conditions that will be satisfied. So there are three conditions that will be satisfied here. Such that the first one, for all AB that belongs to G, we can have f of AB to be equal to f of A, f of V. That's the first one. Then the second one is that for all AB that belongs to G, we can have f of A to be equal to f of B. This implies that A is equal to B. Now this first one is talking about homomorphism. This homomorphism condition. Then this one is 1-to-1. Then we go ahead and check for the onto part. That is for all H that belongs to H, element of this group, there exists G that belongs to G, such that f of G is equal to H. So if we are able to check for these three conditions, then we conclude then f is, then we say f is an isomorphism. It's an isomorphism of G onto H. That is the condition. So under an isomorphism, we test for three things. The first condition is for homomorphism, 1-to-1 and onto, because an isomorphism is a bijective homomorphism. Then the last one that we are going to define, the last type of homomorphism that we define is called an automorphism. This is the last one, the last type that we discussed, an automorphism. So an automorphism is an isomorphism. It's an isomorphism of a group onto itself. Onto itself. So that's very simple. So under automorphism, we have an isomorphism of a group onto itself, just like an endomorphism. Endomorphism is homomorphism from a group onto itself. Okay, so under this automorphism, that's what we are going to get. Okay, so we are going to take about 2 or 3 examples, then we close the class. So now let's take an example. We know the 5 types of homomorphism now, so we can go ahead and take examples. Let's take example. Let's take 2 or 3 examples, then we'll conclude. Okay, let's take example. See example 2. I think we have taken one example before. Example. The question says that we should show that the mapping F such that we have set of real numbers under addition, set of real numbers under addition, the binary operation is multiplication. So set of real numbers under addition, binary operation is also multiplication. Define, show that the mapping F defined by f of x is equal to x squared for every x that belongs to R plus is a monomorphism. Monomorphism. That's what we have to show. So we also have to find F, that is the kernel. If we show this, we first show that F is a monomorphism, then we now go ahead and find the kernel. Of course, what is the definition of monomorphism? A monomorphism is an injective homomorphism. That is, we check for homomorphism, then we check for condition for 1-to-1. If we are able to check for the 2, then we can make our conclusion. Now let's see what will happen. We are given F as what? Set of real numbers under addition, the binary operation is multiplication. Then we also have it as the same thing. Okay, then we know that our f of x is equal to s squared. So the first condition now, we want to show that this is if you are asked to show that it is monomorphism, for it to be monomorphism, we must first show that it's homomorphism. Then monomorphism is an injective homomorphism. We show that it is homomorphism. Then we show that it is also one-to-one. So now let's show that it is homomorphism. We know that f of a will be a squared, and f of b will also be b squared. That we know that. So f of ab will now be what? F of ab will be a squared b squared. That's what we get. That is f of ab. Will it be the same thing as f of a multiplied by f of b? F of a is a squared. F of b is a squared. It's also a squared. Are they going to be the same thing? F of a. No, this one will be f of ab all squared. The same thing as a squared b squared. So are they going to be the same thing? Yes. Then you now say, therefore, no, you say f of a ab is same thing as f of a into bracket f of b. We know that this is equal to this. We have shown that on the board. We just say therefore f is a homomorphism. So that's condition for homomorphism. So we have shown one out of the two conditions. So we have shown that f is a homomorphism. So we have been able to show that. Then we go ahead and show the second condition. So which is one-to-one. So let me clean here. I don't want to write below. So the second condition for this to be monomorphism is that it must be injective. That is, we know that f of a is equal to f of b. That's the condition for injective. F of a equal to f of b implies that a squared is equal to b squared. And of course, what can we say about this? This implies that if you take the square root of both sides, a is equal to b. So it's got to a is equal to b, and that's condition for one-to-one. We now say thus f is a monomorphism. Monomorphism. We have been able to show that f is monomorphism. Then the last thing, the second question is that we should find the kernel of a. The second question, we have to find f, the kernel of f. So how do we find the kernel of f? We must know the identity. Then the question is under multiplication. The identity element is 1. Just say the identity element here is 1. Okay. F of a is equal to 1. What is f of a? That is a squared is equal to 1. If you take the square root of both sides, it implies that a is equal to 1. Since a is equal to 1, therefore the calf f is equal to 1. So the kernel is 1. And that is what we do there. That's what we are going to do there. So we go ahead and take the second question. Then we can just close. At least we've tried. Okay, let's take the second question. Let's take one more question. Then you can just go and look for standard algebra textbooks and solve as many as possible questions. So let's take the second question. So we take the second question. So example 3. The question says that we should show that the mapping f, so this is a complex number under addition to a real number R2 under addition given by f of x plus yi, which is equal to x comma y, because this is in R2. That's why we have it like this. If this is R1, we only have 1. This is R2. You know, we have R tuple. This is R2, so we have 2 coordinates. Okay, is an isomorphism. Is an isomorphism. Okay. So what do we understand by isomorphism? So isomorphism is a bijective homomorphism. So in this case, we test for 3 things. First test that is homomorphism. We test for one to one, then we test for 1 to. So those are the three things that we're going to test for. So those are the three things that we are going to test for. So yes, we have taken one example before. I introduced types of homomorphism. So the other example is second. This will be example 3. That will be the example 3 for today. So what do we do? Just say let A, comma B belongs to a set of complex number with A to be equal to x plus yi and B to be equal to m plus ni, because this homomorphism is defined. It's taken from complex number back to real number, but is in R2. That's why we have coordinates x, y. So R2, we can have R3. So we have x, y, z. That's what we are going to have. But in this case, this is what we are given. So that's what we are going to get. Then the first one, we want to check for homomorphism here. So we just say for all A, B that belongs to set of complex number, can we find f of A plus B? Why do we use plus here? It is plus plus. So we are going to use plus. If it's multiplication, we say f of AB must be equal to f of A multiplied by f of B. If the condition is satisfied, it shows that this f is homomorphism. So f of AB is going to give us f into bracket. What is A? A is x plus yi, then plus B is m plus ni. That's what we are going to have. Then what can you say about this? This is f into bracket. We can, this is addition. We add real to real, complex to complex. That's what we are going to do. Okay? Please look at it very well. Let's look at it very well. We have x plus, A is x plus yi, yb is m plus ni. Then what do we have here? We had real to real, complex to complex. This is real, x, m, complex, complex. So I'm going to have x plus m. That's what I'm going to have. X plus m, then plus this other one is when I'm going to have y plus n. Everything into bracket I. I start to add real to real and complex to complex. At the end of the day, what is f of x plus yi is x comma y. So here I'm going to have x comma m. That's what I'm going to have. I can have x plus m here, comma y plus n. That's what I'm going to get here. So I've been able to show for f of A plus B. So then I'll go ahead and show for f of A plus f of B. That's the second condition that must be satisfied. So if I'm able to get this, then we'll say, we conclude. So what is f of A? F of A is what? F of A is x plus yi. Then plus f of B is m plus ni. That's what we're going to have. Then this same thing as x comma y. Then plus this is m comma n. That's what I'm going to get. Then at the end of the day, I'm going to have s plus m comma y plus n. That's what I'm going to get here. So please look at it very well. That's what I'm going to get. Look at it very well. So what can you say about these two? This and this. Are they equal? If they are equal, it shows that f is homomorphism. If they are not equal, then it shows that f is not homomorphism. So now say since f of A plus B is equal to f of A plus f of B. That is what we are able to say. Therefore, f is homomorphism. F is homomorphism. So we have been able to prove 1 out of 3, because isomorphism is a bijective homomorphism. So we've been able to show 1. So we go to second condition. Want to show 1 to 1. So just say for all A, B that belongs to set of complex number, can we find f of A, which is equal to f of B? So can we find this? Then let's look at what is f of A. F of A will be f of x plus yi. We leave the same thing as f of m plus ni. Let's look at it. Are we going to get the same thing? We're going to look at it. Then what is x plus yi? S plus iy. F of x plus iy is defined as x comma y. Will it be the same thing as m comma n? Then this implies that, in this case now, it implies that s is equal to m and y is equal to n. That's what you can conclude. That's what you get. So it shows that, and of course, so from there, that's what we're going to get. Then from there, this implies that x plus yi is equal to m plus ni. That's what we're going to get, because it is real to real, complex to complex. Then therefore, this implies that a is equal to b. Then f is a monomorphism. F, no, we have to show that f is isomorphism. But since f is homomorphism and it satisfies one-to-one condition, at this point f is monomorphism. Then we go ahead and show the third condition. And the third condition is onto number 3. That is onto. Oh, no. Number 3. That is onto. The third. So we show for the onto condition. If it is satisfied, then we know what to do. We now say for all sy that belongs to R2, there exists s plus yi that belongs to set of complex number such that f of x plus yi such that f is equal to x comma y. That's what you know. In this case now, for all xy that belongs to this, whatever the value of xy is, we are still going to get it in the set of complex number, because set of real number is a subset of set of complex number. Set of complex number consists of 2, real parts and imaginary parts. So without wasting much of our time, this we know that this is going to hold. Then at the end of the day, we now say thus f is an isomorphism. So f is an isomorphism. So I would love to stop here because of our time. Just go through it over and over again. So if you have any question, just write at the comment section. I promise to attend to your questions. Thank you for listening, and God bless you all.
Mathematics made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.